Hello everybody and welcome back to Differential Equations Day 6, Applications, Population Dynamics, and other things which are awesome, like Newton's cooling and whatever. And yeah, so basically this is awesome and it's pretty sweet and it's also delicious. So, let's just rock in, rock out, rock in, rock up, rock down. First things first, let me just give you a little bit of a disclaimer about mathematical modeling in general. It's very necessary to perform proper analysis to your problem. So identify all the acting variables in their relationships. So you need to understand if they are proportional or inversely proportional or what have you. Once you figure that out, you can formulate your equation to express the model. And if you can, find initial conditions. Very important. Look, there is some pretty wicked mathematics when we get the series at the very end, and there is something wicked with initial conditions, which just made my eyes water because it's so badass. But first, we have to do this. Okay, anyways, solve differential equation model and check with any known parameters of facts. Okay, so whatever that means. I don't know what I wrote. I guess just like make sure that it's not wrong. When I wrote this, it was like 2 months ago, because population dynamics. So, exponential growth model. Population with respect to time is P of t. K is a proportionality constant. Okay, very good. So, obviously we can solve this. We all know how to solve this. So if you want to solve for K, which obviously we all want to, let's say, for example, it doubles every 3 weeks. Your population doubles every 3 weeks. That's what we're told. Then n is the amount that it doubles or triples. So in this case, it doubles. So ln of 2 divided by 3 weeks. We'll be doing this in an interval of weeks, hypothetically. So t would be equal to 3. And that is kind of a shortcut. You can solve for it and waste your time, or you can just rock out with this awesome equation. So I recommend memorizing this. Again, if you want to quadruple it over 4 weeks, ln of 4 over 4. Remember that. I think I actually have a proof for that. Population will increase by a factor of n for t time. Let's see what I did here, because I don't remember this. Probably awesome, though. Let's be honest. Check that out. It's pretty sweet. Yep. So natural log of n. And, yeah. So that makes sense. You just solve for k. I mean, pretty sweet. This is with dp, respect to population. Well, the population is doubling with a factor of n, or is being increased or decreased by a factor of n, which is equal to the proportionality constant times time, multiplied by time. Boom. I mean, yeah, rock out. Let's continue, baby. Population dynamics continued. The process of creating a more precise model is called increasing its resolution. So, hypothetically, you're modeling something, and you have this population. We'll just say we're doing population modeling, obviously. In the context, it's better this way to describe it in context, because, it makes more sense. This doesn't account for that much, so we need to increase the resolution. So let's just say this. Now it's got a population ceiling. Okay, so at population n, it kind of starts to teeter out. Okay, and you need a minimum population, as we also have a maximum population, for it to increase. You don't want too few animals, I guess, in the population, or people, or whatever it is, because there are different factors where, if it's not big enough, then they won't survive and multiply, etc. It's pretty sweet and brilliant, honestly. And then, we all know population ceiling. It gets too high. Let's see, it's like environmental science. They start competing for, resources and each other and land. There's so many factors that go into it, which is why let's also throw in some hunting and harvesting, baby. Okay, humans and animals as well. It really just depends on what's being defeated here. Let's just say it's like a bird population, or maybe a snake population that gets eaten by birds. That is the harvesting. They're being subtracted. So it's periodic decrease. Very interesting, guys. Okay. So let's do some interest rate problems. Woo! In how many years will $1 double itself at 4.3% per annum? Awesome. You just kind of take the natural log of 2, because we're doubling it, and at 4.3% a year. So you divide by 0.43 and you get your number. Pretty sweet. Okay, and by the way, 4.3%, you got to shift the decimal so it becomes a proportion. At what interest rate will $3.5 triple itself in 7.8 years? Well, by the way, the first two I chose to be pretty easy, so it's not that hard. Natural log of 3 divided by 7.8. Yes, we all know how to do this. It's pretty self-explanatory. This is just dipping your feet in the water, but let's do some real ones. How much will $1,000 be worth? It's 6.7% interest after 10 years. Well, we have to use our analysis, observation skills. Okay, 6.7% interest, so it's going to be multiplied by the total, which we'll just say P, after 10 years. You just solve for P. P is equal to, like, you know, e to the 0.067t, I guess, times C, $1,000 times that. Let me actually calculate that in Desmos real quick. Yep, and I guess that's why I threw this in, because you... Oh, you know what? Actually, you guys know how this is derived. Completely know how this is derived, because we solved our homogeneous first-order problems. This A is just the constant of integration. Pretty sweet, isn't it? I think so. Okay, so percent. Okay, so yeah, you just solve this as such. This one is going to be pretty difficult. Or maybe not. It really depends. How much money would you need to deposit in the bank at 5% interest in order to be able to withdraw $3,600 per year for 20 years if you wish the entire principal to be consumed at the end of this time? Okay, so I did solve this out. I recommend you get a stab at it. So first you must formulate your problem. And we do have an initial value. Okay, next. This is separable, which is kind of where I actually first treated this not as separable, and I treated negative 3,600 as a function of t, and it was just t to the 0th power, and I solved this as a first-order non-homogeneous problem. And what's interesting is that the answer was wrong until I put a negative sign in or behind the integral, which even when it was in its proper form, so it was a little weird and backwards, and I spent like 2 days looking at why that was, and I didn't figure out why it didn't work like that. And I was like, dude, I'm wasting my time. That's an anecdote. Who cares? But you solve this like a separable problem. Yes. Awesome. We can actually take the 0.05 out and make this 10 times easier. Integrate on the right side, because this is an integral not of 0, but 1 multiplied by dt, so it's t plus c. Next, it's just the natural log, incredibly simple. Raise it to e, and add 72,000, rather. And then we solve for c. And it is awesome, which is this. Okay, so we have all of our values here. Okay, so now, since we already have solved for our initial condition, we just want to see what it's like at time is equal to 0, the initial amount that we put into the bank. It's just plugging and chugging at this point. You can put this into a calculator, and we have our answer, baby.